Okay, so today's class is essentially all about common distributions. So we'll do a couple of the remaining ones, discrete distributions, geometric, which I forgot about last time, then go back to Poisson, spend some amount of time on Poisson. We will cover Poisson in much more detail when you do queuing theory, because it turns out Poisson is much more relevant there. So we'll come back to Poisson. Here it's just, I'm just going to give you like an overview of it. And then move into some continuous distributions, uniform, Gaussian, exponential, and if there is time, we'll do power as well. Otherwise, in the next class, I'm planning to do power, and then we have a few remaining topics, some rules, theorems on limit, on amount, on bounding the tail probabilities of distributions, and then the joint probability and the Bayesian networks. Okay, so let me just start with the first topic, geometric. So a geometric distribution is a discrete distribution. So what it is it has to do again with trials. So generally speaking, when you have discrete distributions, it has to do something with some kind of trial going on. In this case, what you're looking for is the number of failures before the first success. So remember, we have Bernoulli trials. So in a Bernoulli trial, we have probability P of success, and then probability 1 minus P of failure. And when you do binomial, we're talking about the number of trials that we want to do. So I should say, take it back. Binomial, looking at the probability of having, certain number of successes. Let's say you do 100 trials. How many of them are likely to be successful? Let's say you want to say 8 successes out of 100. That would be binomial. We're assuming independence. This is very important. Independent trials. Again, this is something that doesn't always hold in practice. And the reason why it doesn't hold in practice is because independence means that you do the first trial and there is no effect on the second trial. But in reality, the conditions that lead to the first trial very likely hold for the second trial as well, right? So let's say you're, the testing for the amount of humidity in the air, and you do a trial at 9 o'clock. Now you're assuming that the next morning when you do the trial, these are independent events. That's humidity, whatever the value is, it's an independent event. But of course, the weather system that lasts 3-4 days is going to make them correlated. So while we make these independence assumptions for the math to be nice, in reality, independent trials doesn't always hold. And one of the things you really have to be watching out for when you do any kind of study or any kind of research is, are these things actually independent or not? So that's one of the things you have to worry about. Anyway, so assuming they're independent, we essentially have the following situation. You have sort of a failure, and then a success. Okay, and you can have a certain number of failures, and then a success. Now the failure happens. So okay, to come back to this, okay, what I wanted to say was, so geometric trial is the number of failures before the first success. That's what you try and capture. In other words, binomial is how many successes happen if you do so many experiments. Here I'm saying, okay, I'm going to have these failures. What is the first time we get a success? So it's starting at the beginning. So we start at this time, move forward, we get a failure, and a success. So there's 1 minus P, there's 1 minus P, and so on. And then you get probability success as P. And because these are independent events, we can multiply them out to get the total probability. So we get the probability of I. That means that we have the I failures and the first success. Another way of thinking it is that the ith trial is the first successful trial. Okay, that's the way to interpret that. Probability that ith trial is first successful trial is just nothing more than 1 minus P to the I and P. So that's your classic geometric distribution. And, so this kind of gives us the formula. There's not a whole lot to say about this, and probably it's easier to understand what's going on with an example. So let's Oh, I'm sorry. Yeah. I minus 1, right. Yes. Because you have I minus 1 of these, and this is the first one. So let's say we have a link. So this often shows up in networking in the following context. We have a link, and the link has a packet loss rate. How do we get the packet loss rate? Let's say we take the frequentist approach. We send 1 million packets, and 100,000 of them get lost. We'll say it's a 10% packet loss rate. So it's and so we can express this, the loss rate, as 0.1. Now what I want to do is, what is the meaning of a success? The meaning of a success is it gets to the other side. Meaning of a failure is it did not get to the other side. So in this case, 0.1 is the loss rate, and it's sort of the opposite, right? Here, the event happening is loss happening. So instead of the packet failure is an event success, and event failure is a packet success. So what I mean by saying is that 0.1 is the probability of packet loss. Okay, so we can represent it as either P or 1 minus P as you wish. But let's just say that this is nothing more than 1 minus probability packet success. And so it's easier for us to deal in terms of packet successes. So probability of packet success obviously is equal to 0.9. So it's just 1 minus the loss rate. So that's easy. So what I want to do is to find out how many times you need to send the packet over before it actually gets to the other side, right? So I send the packet over, it gets lost, I read timeout, I retransmit, I send it over, etc. I want to find out how many times I need to do it. So probability that it gets through the first time is what it is. P1 means first trial is successful. So that means I just sent it over once. Well, that's nothing more than 0.9, which you get from by plugging in the formula over here as well, okay, because I is 1. And then P2 is 0.1 times 0.9, which is 0.09, okay. And P3 is 0.009, etc. I mean, you can keep doing this. And you can see right away that if you send the packet once, it only has 90% chance of making it. But if you send it twice, you're going to have a success rate. Oops, what am I doing over here? Yeah, right. So the probability that I need to send it twice to make it through is only 9%. Okay, 90% chance it got through the first time. I need to send it twice only 9% of the time. Probability I need to send it 3 times is even less. It's 0.9%. So the probability that I have to send it, let's say 10 times is infinitesimally small. Okay, so even the 10% loss rate, if these are independent events, it's very likely that I don't have to send it very many times. Okay, that's really what's going on. So the expected value of the geometric distribution with parameter P, okay, is expected value of X. Let me just be careful here. So let's say X is geometrically distributed. With parameter P. Then expected value of X is 1 over P. Okay. So in our case, P is 0.9. So expected value of X in this case equals 1 over 0.9, which is 1.1 bar. So basically, we're going to have to, or we expect to send it roughly like 1.1 times. Okay, on average, that's what we expected to send. So a little bit more than once. This is a very interesting result from a perspective of packet transmission. It says that even though we have 10% loss rate, which is considered fairly high, we just have to send a little more than once. 10% more, roughly, 11% more, and we'll actually get it through to the other side. And this is why, at a gut level, this is why timeouts and retransmissions work. Okay, the reason it works is because you time it out, you send it again. If the events are independent, it's a pretty good chance that the second time you're going to get through. Okay? So the first time you're getting it through only 90% of the time, but second time you're probably going to get through because the expected number is only 1.1. Okay, so this is really where that kicks in. Now, I mean, the condition over here is independence, and this is, again, where the weak point of this analysis is. If you have a congested network, you send something in, chances are the congestion persists for a certain amount of time. Let's say it persists for a few seconds. So you send a packet, you time out, you send it again. We don't have an independent trial. The packet loss rate stays high for a reasonably long period of time, so we cannot apply this result anymore. So naively, you'd say, yeah, these are independent events, and so I can do it. Same thing is true for wireless links. If you have a wireless link, it has a link loss rate of, let's say, 5%. You'd say, great, if I send so many, the link loss rate is going to be very low. It's only 5%. I'm very likely going to have to only send one or two, and you expect that the first transmission and second transmission are independent. But if you think about it, why did you lose packets in the first place? It's because maybe you went, on the side of a hill, and you're driving on the side of a hill. You're going to stay on the side of the hill for a long time. So analysis which assumes that these packet probabilities are independent, okay, are actually not going to work. So you can do all the math. You can say, well, the expected retransmission rate is only so much. But in fact, what you're seeing here is bursty losses. You have a loss, then the probability of a successive loss is actually quite high. And you can have 3 losses, 4 losses. So in this case, what you really have to do is to choose the timeout and retransmission so that when you retransmit it, you're outside the previous event, whatever that event is. And so there is a concept of the time scale at which the link is bursty. Okay, you want to time out and retransmit things after the time scale at which these congestion events or loss events persist. So the point I'm trying to make here is that when you look at the geometric distribution, you compute the expected value. You're just looking at the math, it looks pretty straightforward. Yeah, sure, it's only 1.1. But when you start looking at the system and the underlying reason why loss happens, you have to think a little bit deeper about this. You can't just blindly plug in the value and use it. You have to think about it. Okay, and that's what is the difference between studying a geometric distribution in an undergraduate class and then studying it here. Here you want to think about, is it really true? What's really going on? Okay, let me take any questions about this. Yeah?
But by changing the event, aren't you actually changing those probabilities?
I'm saying that the assumptions of the geometric distribution may not hold because these are not independent trials. So what's happening is that the conditional probability of a loss, conditioned on the fact that there's a loss, let's say the loss at time t, conditional probability of a loss at t plus delta, where delta is small, is actually higher than the unconditional probability. That's what I'm saying. So if you don't do anything, you'll say probability of loss is 10%. But if somebody says at time t equals 5, there was a loss, and at t equals 5 plus delta, you're going to have a higher loss rate than 10%, maybe 90%. Okay? So you have to model that. You can't just plug in a geometric and just say, look, I plugged in geometric, I chug away, I get this 1.1, I'm done. Okay? It's not going to work. Okay? So that's what I'm saying. Any other questions about this? Okay. Yes, come on. P is the probability of success. No, this is not. The probability of success is not going down. Remember, I have to interpret. Capital P of 2 is probability that the ith trial is the first successful trial. So if P is large, right, it's going down very fast because I don't have to wait very long before I get the first successful trial. So let's say P is 0.999, then P of 2 means, do I have to do it twice to get the first success? No, I don't. I'm probably going to get through the first time. So as P gets larger and larger, closer and closer to 1, the number of trials I need in order to get its first success goes down. Okay? Or the probability that I have lots of failures before the first success goes down. That's why I wrote this out over here, because I'm using P twice, and it's a bit of a problem. Starting with the Poisson, we'll move from P to lambda, and then life is better. And in the lecture notes, I changed the notation to lambda for the Poisson distribution for that reason. It got too confusing. But for whatever reason, in the literature for geometric, people use small p for the parameter. They don't use lambda. Okay. I mean, why do they do that? I don't know, but that's what they do. And I don't want to. So I'm going to keep you equivalently confused, not extra confused. Yes, you have a question or no? Okay. All right, let's move on to the Poisson distribution. Oh, I should have left it up. Oh, well. Okay. Okay, so the Poisson distribution arises in many different contexts, and as I said, we'll study Poisson in some detail when you study what are called pure birth processes. But here what I want to do is to motivate the Poisson purely as a convenience tool to calculate binomial probabilities. So let's go back to binomial for a minute. So we said we have the Bernoulli trials, and with parameter small p. Now, and also I have something called the number of trials, which I call n. And basically we had the formula that the probability that x equals I is nothing more than n choose I, p to the I, 1 minus p, n minus I. Now this is easy to write, but it's kind of hard to compute when n is large, because you have the combination, we have this one over here, n choose I. For example, if n is, let's say you do 1,000 trials, n is 1,000, and I is, let's say, 200, then you have to compute, so 1,000 factorial by 200 factorial, 800 factorial. And, okay, you can kind of take this out by subtracting it, but still you have a fairly large number of computations to do. And you're saying, boy, this is a pain in the neck. Is there a way to get around this? And the answer is yes, you can get around this. And the way you do it is to use the Poisson. So remember what we have with the binomial, if you think about it, is you have some kind of distribution, a histogram, if you will. You have some central mass, and then it's a little bit symmetric. What I'm going to do is I'm going to show you two different ways of computing these values. Okay. In the first case, what we do is we retain the I as being discrete. So the probability of I, that means you have I successors over here. So Px equals I means we have I successors. We're going to compute the probability of I successors, but we're going to essentially use this trick to compute this very easily instead of having to do all this computation over here, and that's the Poisson. And the second thing, what we're going to do is we're going to take the number of trials, n, as going to infinity. Okay, we're going to infinity. What that means is that then we get a continuous distribution. Okay, when you get a continuous distribution, then it turns out that we can use a different formula, and that is the normal distribution. Okay, so there are two different ways in which we kind of are looking at the approximation to binomial. Okay, so what I'm going to do here is that I assume that we can represent by lambda the product of n and p. Okay, so if n is large and p is small, okay, we need to I'm not saying how large it is or how small p is, but we can kind of just say n is large and p is small. Then we take the product of np, and this is called lambda. And in some sense, this is the overall probability. Let's say you do 1,000 trials and probability success is 10%. Then you expect about 100 things to be successful, right? That's roughly speaking what you want. What you expect to see. So that's kind of NP. That's what your lambda is. Okay, and so what we're going to do is that we are going to write down the Poisson formula. So the probability that we have x equals I, that means we have I successors, can be written instead of this way. We can write it as e to the minus lambda, lambda to the I. I don't need the parentheses actually. Lambda to the I by I factorial. Okay, so we haven't got rid of the factorial completely, but at least it's a little bit less cumbersome than this. And it turns out that this approximation of the binomial is quite accurate. In the homework exercises, what you have to do, and I'll come to homework when you do the administrative break, is that you compute the binomial and the Poisson for small value of n, large value of n, and you'll see that when you have small value of n, they differ quite a bit. But when you have large value of n, actually they come very, very close. It's quite close. So that's one way to understand Poisson. Again, as I said, there are many different ways of understanding it. But to be more precise, so what we have over here, so if you ignore the binomial for now, what we're going to say is that we have a discrete variable, a discrete random variable x, and it has the domain is now it's infinite. Okay, remember that in the case of the binomial, we have n trials, so it's sort of a finite domain, but here we have 1, 2, 3, etc. It's an infinite domain, and it is it has it's Poisson if the distribution looks like this: probability x equals I, e to the minus lambda, lambda to the I by I factorial. Why does it look like this? We'll come to that when we discuss queuing theory, okay? Because then the intuition becomes very clear. For now, all that's important is this is the form. This is what it is, okay? And it turns out that another intuitive way of understanding is like this. Think of the following thing. I have a switch or a router, and then I have I have a bunch of sources that are sending inputs to the switch or a router. And now what I'm going to do is that each source has some intrinsic probability. Let's say there are n of these, and each of them has some probability p of sending a packet into this router. Okay. What I want to do is I want to find out what is the probability that I packets arrive to this router in any particular time period. Again, what we can do is we can say, okay, these are independent trials, and so we can compute the probability that I packets arrive, okay, where p is the probability over some time period that a node sends some data. You can compute over that same time period the probability I. You can define that as a Poisson. So as a more specific instance, consider how the University of Waterloo is set up in terms of its routing. So we have different buildings. So the way it's set up is that on campus we have, 30 buildings. Each building has an access kind of wired closet, and then through that wires go to every room. Okay, and then a bunch of actually what I call wiring closets, just these small rooms. You open it up, it's full of wires, and from there wires go to every office and to labs and so on. Let's consider what happens to all these buildings. They all actually go through gigabit links to a router that's in the basement of this building. I'm probably standing right above it right now. Okay, there's one box over here in the basement of MC, and that's the main campus router, and this has some output link. Actually, you have two links going to two different networks. In case one goes down, you can switch to the other. But that main campus router is below us. Imagine these terminals are, in fact, the endpoints, all the PCs and laptops, etc., in the entire university. Okay? So what I want to do here is I want to model what is the total traffic coming into this router. Again, if I have some way of measuring the probability that over a period of, let's say, 1 minute, a node sends data, okay, and this could be different from different times of the day, that's fine. And these are independent. I assume that people aren't all going to things at the same time. Again, independence is important. Then I can model the traffic coming in over here as a Poisson distribution over here. Okay, and so this assumes that everything is independent, etc. Okay, so because of this, the Poisson distribution is very commonly used in analysis of networking systems, because we typically have lots of sources, and the typical usage ratio of any individual node is fairly small. So until about 1995, this was like the standard, the golden standard. If you want to simulate a network, you assume Poisson process coming in. You choose the intensity by choosing lambda, and then you kind of get the stuff coming in. Around 95, people said, look, is it really true? Is it really Poisson? And in a series of papers, two researchers, Vern Paxson and Sally Floyd, actually started measuring lots of different nodes. And they wrote a classic paper called The Failure of Poisson Modeling. Okay, basically they said, look, all these models assume Poisson are wrong because traffic is not Poisson. And they showed that while we can assume these things are independent, etc., in reality it doesn't work. Everything that you look at is non-Poisson. These are not independent. Just to give you a very simple example, we say that that these are independent events. That means that if somebody here decides to send data, it's unlikely somebody else is going to send data at that same point in time because you have these ratios. However, we have lots of correlated events. For example, this class is, people are in session, nobody's using the computer right now. However, when the class is over, everybody goes to their office, immediately there's a surge of traffic. Okay? Or if you look at, people come into work, at some point, if everybody comes into work, then, there's correlated events. Some news event happens, there's correlated events. So in fact, we find these independence assumptions don't work. So while Poisson is nice and it's in queuing theory, it's actually essential to do anything reasonable. We'll see that. It turns out that in practice it doesn't work. So I'm showing you sort of both sides of the Poisson coin. Okay? On the one hand, it's nice, it's intuitive, it looks pretty good, and it certainly models the binomial, but because the independence isn't true in practice, it doesn't work. So you need to know when to use Poisson. Poisson is useful as like a first cut. Okay, you don't exactly know what's going on, what the traffic is. You haven't measured it. You'll say, okay, let's assume Poisson will get some numbers. These are likely to be off by a factor of 5 or a factor of 10, but at least it's not off by a factor of 1,000. Okay, so that's kind of a rough and ready analysis. You use Poisson. All right, any questions about this at all? Yes?
So the X in this case, the Poisson formula is the number of trials, right?
Number of trials that succeed. Yeah, equivalent to how many packets arrive over here.
Okay, no. So isn't it the number of failures and then I would be the successful?
No, that is geometric, right? In geometric, we say how many successes, how many failures before the first success. In binomial, which is why I started right over here. Binomial, we say I have number of trials n, and probability of success of each is p. I want to compute probability that we have I successes among the n is this formula over here, right? I have to get p to the I successes, 1 minus p to the n minus I failures, and that gives me a probability of I successes. And then I'm approximating that over here, and still I have p x equals I. I want to know what is the probability that we get I successes in this. In these trials. But of course we have, in this case, sort of infinity of trials, but with discrete points. And in the, as I said, in the Gaussian we have a continuous distribution. This is a discrete distribution. Any questions about this here? So let me do a small numerical example just to kind of drive this home. So let's say we have 1,000 endpoints. And we know the probability p is 0.001 that they are going to be active. This is just like at MC. So we have 1,000 servers that are sending data to this router, and any one of them is active at 0.1% of the time. Then we can say lambda equals 1 because you just multiply these out. And now I want to know what's the probability. Let's say that this is 0.001 in any 1 second. I'm giving the time period now, interval. Okay. So the probability that what's the probability, let's say, that we see at least one, okay, so what is the probability we see at least one packet in 1 second, right? So at least one packet at R is nothing more than 1 minus P of 0, right? Probability x is 0, so it's just probability 0 packets is nothing happens, and so 1 minus this. So this is equal to 1 minus. I just plug in the values. It's e to the minus 1, and then lambda is 1, so 1 to the 0 upon 1 factorial. So it's just nothing more than 1 over 1 minus e, which turns out to be 0.64. So there's a 64% chance that we'll see at least one packet, okay, with parameter 1. With lambda equals 1. So 64% chance that the link is not idle. Or you can say even with 1,000 nodes and lambda is 1, there's a 36% chance the link is actually idle. If I just look at it for 1 second, I can just plug this in and get it right out of that. I mean, of course, I can assume it's Bernoulli, etc., and go through binomial and go through that whole thing. But if you use the Poisson, this is what you get. Okay. And there's, I think, one other example in the homework that you should probably try. I should add that even though here I've said that Poisson comes in when the trials are independent, there's something called weak dependency, which I don't fully understand. And the claim is that even with weakly dependent events, you still get Poisson. which is great, but as I said, in practice, nodes events are strongly dependent, and so we don't actually get Poisson, but it's a good rule of thumb to use. Okay. Any questions about this over here? Yeah.
So anything suggested about all this real-world traffic, one which is correlated any model or anything?
Yeah, people have proposed a number of models. Most widely used what I call long-range dependent models, and where they show that we don't have independent, but we have dependency over a certain number of previous events. They define what's called the autocorrelation function, and they look at the degree of autocorrelation over various lags. Okay. The problem is that these are not analytically tractable. So you can use them for load generation. Okay, you can come up with power law or these long-range dependent traffic models, but I can't tell you anything about the output other than the simulation. So in other words, I have this input coming over here. Well, I didn't tell you what the router service rate was, but let's say I choose some service rate. Okay, let's say I can serve a certain number of packets per second. What I want to know is the queuing behavior. Okay, with Poisson, I can tell you the queuing behavior. I can tell you the probability of how many packets are going to be in the queue and the distribution. All right, I can tell you exactly the probability of that, and that we'll study that, in about 2 weeks' time. But with these kind of realistic traffic models, all I can do is simulate it. And then there are many different parameters, how to choose these different things. It gets very messy. So yeah, we don't actually have at this point analytical tools that allow us to compute parameters of interest for these kinds of traffic. So if you're doing simulations, you can use these, what I call LRD, long-range dependent models. Yeah. Any other questions? Okay, let's stop here, and then yeah, I guess I'll continue with the uniform. So let's see, I had a couple of announcements to make, the discrete distributions to continuous distributions. And just to remind you, in the discrete distribution, we compute the probability Px equals I. That is, we have some discrete domain which is indexed by I, and we're computing the probability mass function that you have this value assumed by the variable x. And in some cases, it's the number of successes. In some cases, it's the number of trials to the first success. But we have a number. We have a number of x, number of something. Okay. In the continuous case, we have basically probability that x equals x. This is not really a probability anymore. So we don't want to actually use that x equals x at all. What we instead say is that we have a density function. And again, I've revised the notes just to keep it consistent with standard terminology. I'll call it fx. Okay, and I don't want to use the word p there because it's confusing, as we said earlier. What we can say is that the probability that x1 is less than equal to x less than equal to x2, should make it capital X. The random variable x lies in the range is x2 to x1 to x2 fx dx. Okay, so that is the only definition we're going to get in continuous, which is that we can talk about the amount of probability mass that lies in some interval, x1, x2. Okay, so that's kind of what you need to understand going in. All right, so we're changing our mindset from probability mass at discrete points I to probability mass in the interval x1, x2. Okay? All right, so just to get it clear, let's start with uniform. So uniform is kind of the simplest continuous distribution. What we're saying over here is that we have in some interval a, b, we have uniform probability mass. Okay? How much mass do we have? What is the value over here? Okay, what is that? This should be easy. 1 upon b minus a, because we need to have the total area under the curve to be 1, right? So it's not like the probability of any value over here is b minus a, 1 over b minus a. In fact, we don't have that, but we can, of course, what we're saying is that this holds over here. So this is basically all there is to it. The expected value of x, where x is distributed uniform, is b plus a by 2. This is trivial to show, and sort of fx equals 1 over b minus a. Okay, that's the value of x at any point is 1 over b minus a. I'm just drawing that over here in the range. A less than equal to x less than equal to b. Our old friend, the 0, 1 uniform is just a equals 0, b equals 1 over here. Okay, all right, so this is mostly for you to sort of switch your thinking from discrete to continuous. So let's start with the first non-trivial distribution for continuous, which is the Gaussian, or normal as it's called. So the Gaussian distribution, the way it's represented looks kind of funny, and I'll try and explain to you how it comes about, why it looks that way. But it is the distribution which arises when we have, maybe the easiest way to explain it is like this. You have some chemistry experiment you're doing, okay? So I don't know, all of you probably have done chemistry lab. So I did chemistry lab. I guess these days we have virtual chemistry. Maybe should say, how many people actually did chemistry lab with reagents and titration and dropping stuff in beakers and the color changes and stuff? Okay, all of you have done it. Great. Okay, I even managed to. I won't tell you what I did. Okay, I mixed two things that should not have been mixed together and definitely should not have been heated to high temperature. So it's a good thing my friend did not lose his eyesight. It was actually pretty bad. Anyway, but going back to this, what we're doing is, we have some beaker and we get a pipette and you drop these things in. And what happens is that sometimes it takes 5 drops, sometimes it takes, if you're measuring it's 5 ml, sometimes it's 5.5 ml, sometimes 4.5 ml. And my teacher would get very suspicious. It was always 5 ml all the time because that was wrong. Something was crazy. I mean, you cannot have the exact same value every time, okay? Because there's variability. Your pipette is not exactly the right thing, and the reagent is not exactly the right concentration, and whatever time of day, phase of the moon, we don't expect the same value. So you're expecting to get like 5 ml as the value, but in fact you get one below, one here. You don't expect to get, when it's 5, 20 is very unlikely. So that's called an outlier, and you just take it out. It didn't happen. Okay, that's Las Vegas, right? So what happens beyond 3 sigma stays beyond 3 sigma. But we have a certain number of points. So we find that these variations are such that if you were to draw a line over here, we have a higher probability mass close to the expected value. So if you draw like this, 5 ml over here, you can see that most of the mass sort of lies close over here, and then the further away it gets, it's less and less likely. And people have done this for other things. They measured, the heights of people in the room. If you take everybody in this room, you line them up, you kind of find your heights. You find that there is some mean value, and you're around the mean, and then there's some distribution, around it. And so, shoe sizes, you name it. Any physical, most physical things where you have some mean, some expected value, tend to be around it. Okay, and so this is what's called the normal or Gaussian distribution, and it arises from the binomial when n tends to infinity. So what we're saying in the binomial is that the probability of success of a trial is p, right? We have probability of success of a trial is p. So we have some kind of expectation of how many trials are going to succeed, and that's sort of our mean in some sense. And then we have some variation around it, and so that is the intuitive understanding. And when you go in the continuous case where n tends to infinity, what we get is, in fact, a curve that looks like this. This is the classic sort of bell-shaped asymptotes to infinity on both sides, plus and minus infinity. And this is the Gaussian distribution. So the technical definition of the Gaussian distribution, okay, so we define it as n. We have 2 parameters, mu and sigma square. So mu is the mean, and sigma squared is the variance, and it's defined by fx is equal to 1 over sigma under root 2 pi e to the minus half x minus mu by sigma squared. Okay. All right. So that's one. People write it in very different. Sorry. E to the minus half. Okay. So we essentially are seeing this fx as being defined in this way, and this is sort of sigma root 2 pi over here, this sort of root 2 pi business. So root 2 pi comes because it turns out that integral minus infinity to infinity e to the minus x square is equal to 1 upon root 2 pi. You can actually prove this equality quite easily. And so, is it x squared by 2? I can't remember. I guess it is. I have to remember how to do this. I think this is correct. I may be missing a factor of 2 over here, but the root 2 pi comes from there. Okay. So what we're doing over here is, why we're doing this, because we want this fx to have the property that integral minus infinity to infinity fx dx equals 1. In order to get that property, we need to essentially normalize it, and the normalizing factor turns out to be sigma root 2 pi. Okay. And in one of the homework questions, you will actually use essentially the cumulative distribution and this thing over here to show certain properties of the Gaussian. I highly recommend you try that, because you really understand what's going on with normalization and how the sigma comes over here. That sigma comes essentially from taking the derivative of the cumulative. But anyway, I'm going to leave that for you to figure out. But what we have over here is that, think of this as some normalizing fraction, and then we essentially have an exponential over here, a negative exponential over here, and mu and sigma are normalizing factors. Yes?
I think that might be not 1 upon root 2 pi, just root 2 pi, because then it is
What am I? Yeah, I'm sorry. Yes. Sorry. You're right. It is root 2 pi. Yeah, then we got to cancel out when you do the integration. Yeah, sorry about that. Yeah. So let me come back to this. What we have over here is the x is the, so this fx is that basically px equals x. Okay. Well, I don't want to say that actually, because it's not actually a probability. But anyway, what we have is, you take the random variable, we are subtracting mu from it. So if you look at this over here, the mean is over here is mu. What I call 5 minute is mu, and sigma gives you some amount of tells you how wide the curve is. If sigma is large, then we get a curve that's shallower, that's not like this, and if sigma is small, you get a narrower like that. Of course, as you make it broader, you have to make it lower, because the area is conserved to be 1. Okay, so if we take some variable, and so we're basically adjusting for the mean, and we're dividing by sigma, and actually sigma squared, as it turns out, because we over here. So x minus mu, or sigma squared, is always a positive quantity, okay, because it's a squared, and we're taking e to the negative quantity, so it's small, and we get this relationship over here. So if you view this as being the limit of a binomial, okay, so the NP is going to be the mean value of the binomial, and basically this corresponds to the mu value over here. Okay, that's basically how I get this over here. Now, I'm going to kind of put on my sort of engineering hat now and just tell you how to use it rather than where all this thing derives from. So I'm giving you sort of some intuition about why you get the root 2 pi and what the mu and sigma parameters mean. Mu parameter tells you the center point of the bell, and the sigma square tells you how wide it is. But let me kind of put my engineering hat back on and say, when do I use it? Okay, so let's say I have some value which I'm not really sure of. Okay, I mean, I don't know precisely what it is. Then I can say, okay, I'm going to make it, I assume that it's going to be normally distributed. And the more confidence I have in this, the smaller the value of sigma square is, okay, the smaller the variance is. So if we look at the optimization scenario we looked at over here, and I think this question came up, okay, I have this model, you know, I have to, I don't know the input precisely. The input, I have a fixed parameter, and it's a fixed parameter, some fixed parameter f1 equals 5. Well, that's assuming I know exactly what the fixed parameter is. Let's say I don't know exactly what it is. What I'll then I'll say is, okay, I think it's 5, but it's, you know, maybe a little bit around it. Then I'll say it's actually f1 is not 5, but it's normally distributed as 5, and then sigma squared could be, say, 1, and then I have a little bit, you know, adjustment, okay, into this built-in which says that, okay, the value could be slightly here or there. Now, the analysis is a little bit more difficult because I don't have this constant quantity anymore. Instead, I have to look at the probability using this distribution, but that makes the system more robust. Okay, we're not going to have some specific number put in over there. Instead, you have this little bit of variation allowed, and that's really what this is doing. So in some sense, in a mechanical system, that gives you it's correlated with the tolerance. Okay, if I give you a screw and let's say the pitch is 5 millimeters, it couldn't be 5, a little bit more, a little bit less, but it's going to be within this kind of tolerance. And we want to make sure we build a system, even though it has some little bit of variation, it still works properly. So that's where we use the normal distribution. Okay. As I mentioned earlier, if x is, so here are some sort of interesting facts, I guess. So if x is Gaussian or normal, and normal meaning that this is what we normally expect. Unless something fishy is going on, we normally expect the values to be distributed this way. Then the expected value of x is mu, and the variance of x is sigma square. This is, so the value of mu and sigma square can be plugged right into this over here. And if you want to make something into if let's say y is Gaussian with mu sigma square, then x defined as y minus mu over sigma is normal 0, 1. In other words, a zero mean and has a variance of 1. Okay, so what that means is I can take any value y, if y is defined this way, I can just kind of massage it this way, and it can go as n01. And in the homework, you'll see that if you have something 0, 1, you can make it into any mu sigma square you want by essentially doing the same trick in reverse. And it's a relatively easy thing to prove. And so what this means is that we just have to define the values of the Gaussian for n01. In other words, if your mu is 0, and then we have some kind of sigma square equals 1. And then from that, we had tables, which are called error function tables, because the normal function is also the error function. And we can just look up the table and kind of run this through this, and we will get the value for y for any mu and sigma square, which is, again, something that you tend to do in practice. So you can compute the probability, for instance, that this one over here, let's say this value over here is 2 sigma, and this value over here is 2 sigma on each side. So we can compute the probability that x minus mu is greater than 2 sigma. Okay, so what does it mean? It means that I have, what is the probability that a Gaussian distributed variable with mean mu is going to lie more than 2 sigma out on each side? Okay, it means it's going to be far away. That's what it mathematically quantifies the meaning of far away. We can actually write that down, and let me just do that over here. So we can just say that the probability that x minus mu is greater than sigma, it means it lies plus minus sigma, is actually I should say less, equal to sigma is about 68%. Okay, probability that x minus mu is less than or equal to 2 sigma is 95%, and probability that x minus mu is less than or equal to 3 sigma is equal to 99%. It's 99.73. So these are numbers you need to memorize more or less. It tells you the confidence. So that the value of the variable is within 1, 2, or 3 standard deviations from the mean. Okay, so this is how it shows up in reading a research paper. So in many research papers, we see the following: here is the performance of system A, and here is the performance of system B. All right. So if you see this A and B, and here's some parameter, and higher is better, well, you'll say, oh, A is better because across the entire range of parameters, A is better than B. Okay, so the first thing about this is that, well, did they only do one run for each thing? If you do one run for A and one run of B, okay, maybe A is better than if you B for just one run. We have no idea, okay, whether it's always better than B. It could be that, A got lucky, okay. So what you want to do is to mark the, what I call the confidence intervals, which is defined as, and we'll get more precise about this when you do the statistics course, but it's defined, roughly we define it as, we have to actually specify that it's 1 sigma, or 2 sigma, or 3 sigma, but let's say these are 3 sigma values. What this means is that in this envelope, roughly speaking, the 99% of the probability, 99% of the time that you run the experiment, we expect the values to be in this range over here, and 99% of the time that you run B, we expect the values to be over here, if it's 3 sigma confidence bonds. If there are 1 sigma confidence bonds, they're only 68%, they're going to be over here. So if you run the experiment over and over again, okay, so these ones, clearly the confidence bonds are not overlapping, so we can say that, yeah, A is definitely better than B. But suppose you had the same exact curve like this, A was like this, and B was like that, and we found that A, for some reason had very high variations, and B also could have very high variations, okay? This is the same curve, right? If you just show the means, you think A is better than B, but with this kind of variability, we can't say anything about A and B, okay? Maybe they're the same thing. We just run, and, in some cases, B will actually turn out to be better than A, because sort of the envelope for A is something like this, and the envelope for B is, is something like that. And there's certainly zones where A and B are indistinguishable, okay? So we cannot say anything about A and B. So if you are reviewing a research paper, and you will be asked to do that more than once in your career, okay, an easy way to kill a paper is you look at the results, and you say, oh, there are no confidence bonds. These results are meaningless. Trash it, okay? It's easy. You can just say, these results are meaningless. I have no idea what they're talking about. In fact, they don't know what they're talking about either. Conversely, if you submit a paper with no confidence bonds, your paper should be rejected, because you don't know what you're doing. Okay? So you have to have, when you have an experiment, you have to run it more than once. When you run it more than once, you've got to have these confidence bonds. And then you can only make statements. Again, we'll be more precise with what this means when you study statistics. We can only make statements about the relative superiority of A to B if these confidence intervals don't overlap. Okay, and there's a bit more to it, but at least roughly speaking, if they overlap, you're out of luck. Okay, you can't really say A is better than B. Okay, so this is one reason where normal distribution comes up. What we're doing over here is that we are actually using the fact that A, we're assuming that the mean value of A is Gaussian distributed. And again, this is a very famous theorem. We'll come to it in the next class. And but we're saying essentially over here is that if the mean value of A is Gaussian distributed, then I can use the Gaussian to compute the confidence that it lies in this range. And if these confidence intervals overlap, then I don't really have a good idea whether it was just luck that A outperformed B or not. Okay, so this is kind of practical advice that you should use in your research. Okay, let's see. I have a couple more facts I wanted to write down. Then we'll take a break. So, what did I say over here? If X is Gaussian, X is distributed normally with mu sigma square, then AX plus B is distributed normally with A mu plus B and A sigma or A square sigma square. And also if X is distributed normally as mu sigma X square, and Y is normally distributed as mu, I should say mu X, mu Y, sigma Y square, then the sum of the thing, X plus Y, is distributed normally with the mean as just the sums of the mean, which is nice. You can just add up the means together. And in fact, the variances add up as well. Sigma X square plus sigma Y square. And X minus Y is distributed normally with mu X minus mu Y. And but the variance still adds up. Okay, so if you add these two variables, whether you add or subtract doesn't matter. The variances still add up. Yeah.
The second line for
This one. No, this one.
Yeah, it should be A mu plus B.
Oh, I'm sorry. A mu plus, yes, sorry. A mu plus B. Thank you. Correct. Yeah. Okay, so this tells you how to add and subtract Gaussian variables. And the nice thing is you add 2 Gaussians, you get a Gaussian. You add subtract 2 Gaussians, you get a Gaussian. You have to worry about the variance adding up. It actually gets more dispersed in some sense when you add 2 things. But this allows us to kind of start dealing with Gaussian random variables in a fairly straightforward manner. Let's see. There is a numerical example in the lecture notes, which I'm going to skip because it's pretty straightforward. I'll just stop you. Are there any questions about this at all? Or? Yes?
Well, I guess it's possible to some kind of extend this distribution to discrete.
That's a binomial. Binomial is the discrete version of the Gaussian.
Binomial is not defined for negative integers.
Oh, yes, that's correct. Yeah. But yeah, for positive integers, if you move the mean out, so there is something called the negative binomial. And but yes, Gaussian is just defined with on minus infinity to plus infinity, and of course binomial is defined for positive quantities because it's a number of trials. So the equivalence is not exact, but if you take large and you kind of get the same kind of curve, that's the motivation in some sense for the Gaussian. I'm skipping over many details over here because it turns out that you can actually find books on Gaussian. There's a lot more stuff over here. Then I've done it over univariate Gaussian, for example. You can have multivariate Gaussians, and there are many other interesting things, inverse Gaussians, and so on. But this is very fundamental stuff. Okay, so yeah. Yes.
If we take this expression x equal to y.
X equal to y.
Then
yeah.
You get as variance to sigma squared.
Yes.
But if you use a formula 4.
Formula 4.
Get 4 sigma squared.
Okay, let's see. So you're saying okay. Interesting. So you're saying if x equals y, okay, so x equals y, so 2x should be distributed 4 sigma square, right? And 2 mu 4 sigma square because it's a square sigma. That's what you're saying is from formula 4. And okay, and then this one is saying if x plus y should be sigma x plus sigma y squared. So did I get that wrong? Let me see. Yeah, that. Why is that not working out? X plus y. So I'm getting essentially 2 mu again, which is good, but I'm getting 2 sigma square. So I'm clearly wrong. Okay, now I don't know why I'm wrong, because again I used the standard reference for this, but it's quite possible I goofed up. So I can't solve it in real time. I'm going to. Does somebody else have the answer?
Actually, I'm not quite sure because I know Poisson plus Poisson is still a Poisson process, but for normal, maybe normal plus normal, if they are independent,
yeah.
it may be chi-square distribution. I'm not quite sure.
Yeah, actually.
I didn't remember actually chi-square is kind of normal distribution.
Yeah. Yeah, that's right. They're not independent, so maybe that's what's going on. Right. So we are assuming x and y are independent over here. Of course, x and x are not independent, right? So what you're saying here is that, yeah. So yeah, this in some sense is incomparable to this because y is not independent. I can't. Okay, so I know I derived this myself, so I know this is correct. Okay. This one will assume to get this 2 over here, we need to assume independence of x and y, because what we're going to do is to take the density functions, and then we compute the events. We're going to have to, I think we'll have to assume independence for this to work, and this is not independent. Yeah. Yes.
For some reason, I think for the mean value, we should go for in 5. In 50.
5.
We should go divide by like mu x plus mu y.
I don't.
Because if you have same mean, then mean afterwards will remain same. Like if 2 distribution x and y.
You're adding the 2 random variables. We're looking at the distribution of x plus y. So the means should be added up, right? If I have variable which has a mean of 10, other has a mean of 5, the distribution of x plus y should have a mean of 15. So that's correct. It is x plus y. But I think the independence really is what's going to happen over here. Let me double check on this, but that's a good point. Okay, so it is required that x and y are independent. Otherwise, this formula doesn't work. So I should have said that x and y have to be independent. Okay, I will double check that, but I'm pretty sure that is the reason why these formulas don't look the same. But I had not actually put those two together, so that's what happens when you teach a grad class. You learn something. Any other questions about this? Okay, let's stop here for a minute, and in a different context than the normal. So in normal, as I said, we have some kind of expectation, some mean. This is where it is, and things are going to be varying around it, right? In the exponential, we have a slightly different setup. What we have is essentially that, yeah.
One question again. I think your xy independent thing is correct.
Yes.
The second formula you gave is correct, because if they were not independent, you can't just write the variances. You have to give a matrix.
Yes, that's right. Yeah, we look at the joint distribution, right? Yeah, that's true. Now I know they have to be independent, but yeah.
That was a problem. That's
Yeah. Yes, that's correct. Yes, I do agree with that. That's why I said earlier the reason the formula for 2 doesn't work. There isn't an apparent contradiction because of the independence is not being held. Obviously, when you have x and x, yeah, that's good. Well, I should take that off. You're saying yes. There. Thank you. Now we can come back to the exponential. So the setup for exponential is something like this. We have something that where the probability that is decaying over time. So, in some sense, the things should happen. I should be very careful how I state this. As time periods get longer, okay, the probability that we are going to have let me rephrase this maybe slightly differently, okay? So let's start the geometric. The geometric case, what we're saying is we have the certain number what is the number of failures before the first success, okay? That's geometric, okay? Let's take that in the continuous case. So what we have is we have some event has happened, okay, at some time 0, and what we're trying to do is how long do we need to wait before the next event, okay? So in some sense, we have this notion of this inter-event time, which is continuous, right? Time is continuous. So in the geometric, we had this case of, you're doing trial, and failure, first success, right? If you take that the continuous case, the limit, what happens is you have an infinite number of trials, right? And we are going to wait, and then we get a success. So classic example of this is customers entering a bank. So I have a bank or any service center, whatever, and the first customer enters, and then I'm going to sit there and I'm going to basically wait until the next customer comes in. So this is the first customer. I can just add arms and the legs, and there we have a customer. This one has a pointy head, and I want to see the inter-arrival time. So the x equals this equals this value x means that the inter-arrival time between these two customers is x. And so the exponential is very closely related to the geometric. It is the geometric as we take the number of trials going to infinity. So essentially, as the number of trials goes to infinity, so the analog of the first success after many failures is nothing more than the first event happening after some period of time. Okay, so that's the change that we have to make over here. And if you do this, then the probability of the random variable or the density function is given by fx equals, there's a parameter lambda, e to the minus lambda x, if x is greater than or equal to 0, otherwise it's 0. Okay, x less than 0. So it's only defined on the positive x. Obviously, time is always going to be positive. and it's given by lambda e to the minus x. And clearly from here we can see that the cumulative distribution function fx is going to be given by 1 minus e to the minus lambda x. Okay, that's just the integral of that from minus infinity to x. And this, in fact, is the one that we normally use. The density function is not particularly useful. This one is quite useful. For example, f of 0, okay, so I should say, to be more precise, fx of x. So x is exponentially distributed, let us say, with parameter lambda. Then fx of 0 is 1 minus e to the minus lambda. Oh, minus e to the minus 0, oops, minus e to 0. Okay, it's, what am I doing over here? Yeah, 1 minus e to the, yeah, so fx of 0 is, right, I wanted to get fx of 0 equals 0, 1 minus e to the, yeah, minus 0 is equal to 0, but I wanted to actually, okay, yeah, I'm going to come to that in just a second. Okay, I'm getting ahead of myself, which is not good. The other part that's important is that, let's not look at fx0, what I want to look at is, if x exponential is lambda, then expected value of x, this is really what I wanted to say, is going to be essentially 1 over lambda. So that is the important parameter over here. So, did I do that right? Yep, and the invariance is 1 over lambda square. All right, so this is actually what we end up using a lot, is that if we are given exponential and we're told that the mean of this exponential is something, right, then the parameter is just the inverse of the mean. Okay, so for example, if I tell you that customers arrive to the bank with a mean of 3 minutes, okay, and it's exponentially distributed, then I can tell you right away that it's the density function is basically lambda e to the minus lambda x, where lambda is 1 over 3. So the mean and the lambda are inverses of each other in this case for the exponential distribution. And this is really, so the f of x over here is basically going to look something like this. Okay, it kind of asymptotes to 1. Obviously, it goes to 1 at infinity, and over here it's going to be 0. Okay, so we have this exponential rise, as we call it. So it goes up fast, and it kind of tapers off, and eventually it gets to 1. So 1 minus e minus lambda x is what it looks like, and then the lambda sort of controls how fast we get up to the value over here. Okay, so right. So the important parameter over here is, like, let's say the mean is lambda. Okay, the mean is let's say the mean is 3 minutes. So what we can do is we can start using this to come up with some interesting questions. So let me actually give you an example of this. So let's say that the length of a phone call is exponentially distributed, and the mean is 3 minutes. Okay, so let's think about that. What we have over here is that this is not, instead of customers arriving, what we have over here, this is the start of the call. Okay, and instead of looking at the inter-arrival time now, what we're looking at is how long does it last. Okay, and this also is exponentially distributed, right? So we can look at the distribution of the length of the phone call. Okay, it's a continuous variable, and think of the geometric analogy. In the geometric analogy, we have the success and failure. So let's say that failure means the call did not terminate. Okay, and success means it did terminate. In the geometric case, we have to say did not terminate, did not terminate, did not terminate, did not terminate. Okay, terminated. That's my geometric. In the exponential case, I'm saying it continues, 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 and then it stops. Okay, so the distribution of this is exponential, means that we can actually just look at this in this fashion. So the length of the phone call exponential mean is 3 minutes. So we can immediately say that the lambda for this is 1 over 3. Okay, so I can say what is the probability that call lasts more than 6 minutes? Okay, so this is going to be basically 1 minus f of 6, right? Because f of 6 is minus infinity to 6, so 1 minus that is a call lasting more than this, and this is going to be nothing more than 1 minus e to the minus 6 over 3, because lambda is 1 over 3, and this is e to the minus 2, which is 13.5%. Okay, so immediately we get these kinds of numbers popping out, which is great, because I just told you it's exponentially distributed call length, 3 minutes. Right away, knowing it's exponential, I can tell you there's roughly a 10% probability it lasts twice as long as the mean. Okay, and this is quite useful. You're doing some sizing. You can say, okay, we can look at the interarrival of cars on the bridge. We can look at the probability of packets coming to a queue. We can look at the length of phone calls. We can even look at these distributions of how long a packet is serviced. Okay, how long something gets serviced, how long a customer is serviced in a bank, and all of these things tend to be exponentially distributed. And the intuitive way of thinking about it is that at every given moment in time, we have a constant probability that we're going to finish the job. Okay, whatever the job is. Okay, in the case of call, at each infinitesimal amount of period of time, I have a constant probability that the call is going to terminate, which is equivalent to the constant probability that a trial is success or failure. Okay, so if you take a customer, right? Customer is being serviced at a teller at a bank. If I take it any moment in time, small interval in time, it's a constant probability that at that time the customer is going to finish service. If we have that, then the distribution is going to look exponential. So this constant termination is the over the entire duration is the key to the exponential distribution. And again, as I said, it comes directly from the analogy with the geometric. Okay. So if you have this constant termination time, then we get this. And then we get another property which is very important called memorylessness. So let me explain what memorylessness is. Okay, let me give first the intuitive explanation, then write down the math. So you go into a bank, and there's a teller, and the teller is servicing one customer, right? Servicing customer, and you say, well, I don't know how long it's going to take. Okay, I don't know how long it's going to take. So, okay, let me just sit and wait. So you go there, you sit and wait, and it takes, I don't know, 5 minutes or 10 minutes, and you get service. Now, suppose you come in and your friend comes in at the same time. Okay, both come in the bank, both come to, and you see that there are, two tellers who are there, and they're both servicing customers. All right. Now you say, look, I'm just going to wait. And I'm going to go to that line. I'm going to wait for that first customer. And the second person says, oh, that guy is busy. I'm going to go to Starbucks and get some coffee. Okay? So he goes, comes back and has a cup of coffee, and you've been waiting in line the whole time. Now the question is the expected remaining time for you to get service longer or shorter than the expected remaining time for him, assuming that the tellers are still busy servicing the customer, right? Okay, so what happened, you went in and you waited in the line the whole time, and this guy went out and got a cup of coffee and came back and did not wait in line, and the same customer is still there in both cases. What do you expect? Okay, and it turns out that with exponential, the fact that your friend went and got a cup of coffee and came back does not affect the remaining service time. Okay, now this may be either deep or trivial, depending on how you look at it. Okay. What's going on is that when the customer is in service, okay, when some customer is in service, okay, the expected remaining waiting time over here, which is when that customer is going to finish, or, if you think about it, the length of this interval, the remaining time is memoryless. You don't really know whether the person went a cup of coffee or not. Okay, it doesn't matter. You can go, but I mean, conditional that the customer is still receiving service. It doesn't matter. So that's what memorylessness amounts to in this particular case. And we can express that as the following. Let's say that this customer has received S amount of service, and we want to find out the probability that it's going to take T more time to finish service, right? That's basically what it is. The waiting time is just the duration of customer service conditional that they've already received S amount of service. So we can look at probability that the random variable X is greater than T plus S, given that X is greater than S, because it's finished so much of service. It turns out to be nothing more than probability that X is greater than T. Okay? So what that means is that even though this is offset of S seconds, it doesn't really matter. Okay, in the notes, by the way, I've written T greater than T. What I really wanted to say was S greater than T. It's a typo in the notes. So this mathematical equation really says that the previous customer has spent S in time, so we know that our random variable is longer than S. Okay, we know that for sure. It's conditional. Given that it's longer than S, how much longer do I want to wait? It's as if the customer really wasn't there. You started exactly at this time, okay? Because the new guy coming in, your friend who had a cup of coffee and came in, he's going to have to wait only T, and you have to wait this much, and it's both the same. Okay. Another way of looking at it is like this. So we have the cumulative distribution looking like this, right? It's basically 1 minus e to the minus lambda t, or lambda x over here, and this is x on this axis, and this is capital F of x, right? So this is clearly the right-hand side of the curve. Px greater than t plus s is sort of the area under the shaded area of this curve over here, okay, where this is sort of t plus s. So what we are saying is this: conditional that we are in this area, the probability that sorry, I should put s over here, and I have some value t over here. So the reduced sample space, in conditional probability, what do? We shrink the sample space. We take out all the elements in the universe of events which are inconsistent with the condition. What is the condition over here? X is greater than S. So we forget this part of the space, and we're looking at this area over here. So what is the probability that the variable is greater than S plus T? That means it lies in this shaded zone over here. The double conditional that is greater than this, it turns out, is the same as Px is greater than T, which is T over here. What I'm saying is that if I take this double hat space and I divide it by this, it has the same shape as it started out in the beginning. So I take this part, and this slope, so to speak, over here, this is the same as that, scaled up. Okay? And the only distribution which has this property is the exponential distribution. The only distribution which has this property, which we call memorylessness, which is precisely meaning this, is the exponential, and which has this very practical, intuitive connotation. That is that if the service hasn't ended, I really don't know how long it's going to take anymore. It's as if the fact that I got here now doesn't really matter. So to take another variant of the same thing, when I go to the bank and the customer is being served ahead of me, I have some expectation it's going to take 5 minutes, 10 minutes, 20 minutes, which is it's exponential. It doesn't really matter when the previous customer got there. If that previous customer got there now, or 10 minutes ago, or 100 minutes ago, or a year ago, it doesn't matter. The expected time I have to wait before I get service is still the same. It's still the same exponential distribution over here. Okay, so that is the intuitive and the mathematical definition of memorylessness. Okay, are there any questions about this over here? So yeah, go ahead.
Yeah. So if I go to the bank, for example.
Yes.
And my expected wait time is 5 minutes.
Yes.
So after 5 minutes, my expected wait time is going to still be 5 minutes?
Conditional that your customer, the person in service, is still in service. Right? The remaining service time. See, if the person ahead of you is going to be the only, we're assuming, right, in this very simplistic case, there's only 2 people in the queue. There's a person getting service and there's you. Right? Actually, there's a whole queue ahead of you. We'll ignore that for now. Queuing theory, we'll study that, but now we won't, right? So if your expected waiting time, 1 over lambda, is 5 minutes, right? No matter whether the person ahead of you got there now or 20 minutes ago or whatever, it's still going to be, expected waiting time is going to be 5 minutes, okay? Because that's your waiting time. So that's what it means by memorylessness. Okay, we can forget about all past history. Okay, we can just reset everything to now, and conditional on this, everything is going to be just the same as it was. So basically, it says forget about the past. It doesn't really matter. Okay, this does not true for Gaussian distribution, for example, or any other distribution, uniform distribution, right? For example, uniform distribution. Let's take that case. Let's say that you have uniform distribution of waiting times, and okay, so that means, and it's a range A, B, right? Where B is, let's say, 10 minutes. So if you know the customer arrived at 9 minutes, we know that they're going to end by 10 minutes because that's the end of the support of the distribution. It's going to happen, right? The next 1 minute, they're out of here. So you know for sure you're not going to wait more than 1 minute. Whereas exponential, you don't have that, right? You don't have that upper bound. You just say, well, it's as if I just got here and I don't know what happened, how long the previous person was there. And that's why it's memoryless. Whereas any other distribution will not have the memorylessness property. So in other words, the knowledge of the past is going to give you some influence on the future. Whereas in memorylessness, we have no such influence. So that's what makes it analytically quite nice, because you don't have to worry about the past. You have a question? Or? No? Okay, so I have another example of memorylessness, which I guess I'm going to skip over here. So let me just summarize what we went through today. So I started out with the geometric discrete distribution, where we had this notion of independent trials, and we're looking at how many failures until the first success. And that is a very simple formula that's geometric. And we looked at the correlation to that with the exponential. The exponential basically says, instead of having uniform trials, I have this sort of uniform rate of completion of job. And I want to see how long the job lasts. Because I have in any infinitesimal, if the job completed or did not complete, and I have this constant going over here, constant rate. And that is the equivalent of independent events. Then we looked at Poisson, which I introduced here essentially as a trick or a computationally efficient way of computing binomials, okay, easily. But as I said, later on we'll see it shows up in other places, and it has some other nice properties. The uniform are simplest continuous distribution. The Gaussian or normal, which is again taking the binomial and looking at an infinity of events. Of course, also assuming we're going into negative space as well as positive space. You're looking at negative and positive, whereas binomial is only positive. And we had some properties of the Gaussian or normal, and we use it when we assume certain amount of jitter around some mean value. So that's your Gaussian. And finally, the exponential, which is telling you how long do you need to wait before something happens. How long do you expect to wait? And which has this very nice memorylessness property that says how long you need to wait is relatively independent of what happened in the past. In fact, conditionally, it's completely independent. And then I have we'll talk about the power law and so on next time. So I would highly recommend that you take the time to look at the homework questions and at least go through these ones in the assignment, because it will really help you sort of fix these ideas. You have to go from the triangle on the board to the triangle inside your head, okay, and you have to do that through the homework. Okay, we'll stop here and we'll continue with power next time.